Okay, we're back with lab number 5, which is all about double replacement reactions. And hopefully last week went well for you. You had your practicum, a multiple choice test, and just 10 questions. And I also graded your data sheet as part of that. You had to watch some videos on flame analysis and answer questions based on that. This week again, we have some videos that you can watch under supplementary resources on Blackboard. It's all about double replacement reactions. So I'm going to be doing some examples on the board, which I conveniently have in my house, strangely enough. There are 3 major types of double replacement reactions. So I'm going to teach you about those right now, and then we're going to have you do just one at home, one very popular one that you've probably done before maybe, or maybe not, using baking soda and vinegar. So the common ingredients for a volcano that you would make at home. And we are going to be using that again later in the semester to do another experiment. So it'll be your first introduction to that reaction. So type 1 double replacement reactions, they involve the formation of a precipitate. So the basic idea for double replacement is that you're reacting 2 compounds together. Each one contains a cation and an anion. You always write the cation first. That's important to remember, and we'll be talking about this in the lecture as well. The cation always goes first. I'm going to underline both cations. What does a cation mean? It means it's positively charged. That binds with a negatively charged ion, making a compound that's neutral. It's important that the compound is neutral, otherwise we would see a charge written as a superscript. So, the way that the double replacement reaction works is that actually the cations just switch places with each other. You can think of it kind of like square dancing. You swap partners in the process, and I think there's a video under supplementary resources or the extra credit project that shows the idea of, actually I'll post it here. I'll post it here with this lab so you can look at it. That kind of relates double replacement to square dancing, which is interesting. So you can either just take the cations and swap their places, making Cb and Ad, or you can look at it like this. Outers go together and inners go together. So the product then would be Ad plus Cb. That's the basic idea of a double replacement reaction. So type 1 is when one of these products that forms actually is a solid, and you will see it precipitate in whatever test tube you do the reaction in. So let's say we mix these 2 solutions together into a test tube. If we were in the real laboratory, you'd be using test tubes. Here at home, I've just got a large glass container that you'll be watching the reaction in. And you'll be seeing videos online of precipitation happening. You're mixing 2 clear solutions together, clear homogeneous mixtures together, and you'll be seeing in type 1 reaction some kind of precipitate forming at the bottom of the test tube. That's considered type 1, and you'll be watching some examples of that. Type 2 is an acid-base reaction. So I'll do an example of a type 1 reaction, and we can figure out, using our solubility rules, what would be the precipitate. So let's do a real example of that. We're going to take, actually I'll leave that on the board and I'll write here so you can see. We're going to take lead nitrate, and we've been practicing with naming in class. Plus potassium chromate. Now we have to recognize where the ions are. So here, our cation is lead, and our other cation is potassium, and they're just going to swap places. So here, nitrate always has a -1 charge. The fact that we need 2 of them means that lead here has a 2+ charge. So potassium always has a 1+ charge, and the fact that we have 2 of them there means that together they're giving a 2+ charge. So we can directly swap these cations to make our products. So that will leave us with, and I'm just going to write it below so we have more room, that will leave us with potassium nitrate. Notice I didn't put K2NO32 because that would be redundant. We actually compare a +1 and a -1 directly together, but we have 2 of these and 2 of these, so we end up making 2 of that compound. This is a common mistake that people make, keeping the subscript with the ion, instead of realizing that if it's a 1-to-1 ratio, you can just put those ions directly together and put the 2 out front. There is a sheet of practice double replacement reactions in your lab book. So I recommend you work on that to get ready for your exam. And you're welcome to send them to me. I can check them, give you comments, send a picture of it. So this is one product. Based on our solubility rules that you have on your periodic table, or in the back of your lab manual if you bought one, you'll be able to tell what's soluble. So nitrate, I see rule number 2, is always soluble. This is aqueous. And our second product will be lead chromate. And those go directly together because chromate has a -2 charge. You can always check that on your periodic table. It will show you the charge. Or you can infer it because you know potassium is a group 1 metal, has a +1 charge. We have 2 of them, so we have an overall charge of +2 coming from this, so chromate must be -2. Likewise, we were just talking about how we figured out that lead had a +2 charge because nitrate has -2 when we have 2 of them. So therefore, lead and chromate will go directly together. And based on our solubility rules, we can see that chromate is insoluble. That's rule number 6. So this would be our solid. That would be a precipitate that you see at the bottom of your test tube. Okay, so these are type 1 reactions. Type 1 double replacement. Type 2 is acid-base. So I'm going to show you that. It's still based on the same concept of the ions swapping places. So I'm going to leave this demonstration here. Now, type 2, acid-base, always has to involve an acid and a base. So the acid we can identify because it always has hydrogen written first. So the cation is hydrogen. Let's use the most popular acid-base combination, hydrochloric acid, HCl, plus sodium hydroxide. And again, here are our cations, and they're going to swap places. So the ions that compose these 2, we have +1 charge on hydrogen, -1 on chloride, +1 on sodium, -1 on hydroxide. This is a polyatomic ion. You should be studying these polyatomic ions. You have a sheet that lists polyatomic ions and elements that you should be learning in your lecture course. Make sure you're studying that. Also, just familiarize yourself with, on your periodic table, that small table at the top that lists the polyatomic ions. I would be studying that so that you recognize them. Because hydroxide travels together, just like we saw chromate before. It has a -1, and you want to, that should stand out to you, so that you don't get confused when you see that. Okay, so when we swap our ions, the product is sodium chloride. Remember, we write the cation first. That is table salt. And I see a lot of students writing HOH. That's the way you initially put it together, cation, anion. But think about what is HOH? What's an easier way to write that? It would be H2O. We have 2 hydrogens and 1 oxygen. We always write that as a liquid unless otherwise indicated. And sodium chloride is aqueous. So, the major thing about acid and base that should stand out to you, how you identify it, is that one of the products is water, because your hydroxide group from the base bound with your hydrogen from the acid. And those two together make water. Other reactions can create water, so you want to double check that indeed you do have an acid and a base. So look for the H out front on one compound, and look for the hydroxide, the OH group, on the other compound. So that is an acid-base reaction. It also releases heat. So if we were doing this in the lab and you were holding the test tube in your hand, you would feel like it warm when those two solutions mix together. Now type 3 is the generation of a gas. And that's what we're going to be doing right now, using vinegar and baking soda. So now type 3, still the same principle, still double replacement. Okay, so we're back with our demonstration. This is type 3 double replacement reactions. So before I write it on the board, I want you to witness the creation of a gas. So this is type 3. The first, type 1, was precipitate, formation of a solid. Type 2 was acid-base, creation of water and heat by mixing acid and base. And type 3 is the creation of a gas. So here I have baking soda, sodium bicarbonate, and I'm going to put it in a container. I'm going to use a lot of it. You can do it on a small or as big of a scale as you want to, but make sure you're ready to clean it up. So I have a lot of sodium bicarbonate here in this glass container, and this is white vinegar. It's very inexpensive. You can get it at any grocery store for $1 or $2. Same thing with baking soda. You're going to have to go get those materials yourself, and when you have it, you'll be using it more throughout the lab. So a good investment, and also really helpful for cleaning. Baking soda is a good abrasive for scrubbing anything, and the vinegar, with the production of carbon dioxide, helps to clean as well when you mix it together. Vinegar also is a good cleaning material for everything as well, windows, etc. So we're going to mix the acetic acid, which is vinegar, into the baking soda, and we're going to watch what happens. So immediately we see the generation of a lot of bubbles. And can you hear it? It's fizzing. It's creating carbon dioxide, and that fizzing and the bubbles, they go down eventually, but the bicarbonate I can still see on the bottom, so I can add more vinegar. And again, we're bubbling over even, making lots and lots of water and carbon dioxide. That's a good reaction. That's a really good demonstration of the production of a gas using two binary compounds, and it's a double replacement reaction. So I'm going to write that on the board. Always put the top back on your chemicals, even when you're working at home. Okay, so we've just observed the mixture of vinegar and baking soda, and you saw the production of lots of bubbles, the production of a gas. So that is a type 3 double replacement reaction, the production of a gas. So I'll show you the reaction that you just performed. Acetic acid is often written as CH3COOH. The different thing about that is that H is the cation. It's not written first. And that's just because the molecular structure of acetic acid is a very common acid that chemists use and that's used in metabolism in the body. This is what it looks like. 2 carbon groups. There are 3 hydrogens here connected to that carbon. We have an oxygen and then a hydroxide group here. This hydrogen often comes off the hydroxide, making it an acid. When that comes off, it acts independently as H+, and this oxygen is negatively charged, making this whole group, this whole CH3COO group, the anion with a -1 charge, and the hydrogen, the cation, with a +1 charge. So this is acetic acid, vinegar. And we're mixing that with sodium bicarbonate. That's baking soda. And we know from our polyatomic ions that you've been studying. Carbonate is -2. We also know sodium is +1 and hydrogen is +1. So together, with 2 +1s and a -2, this is a neutral compound, and a -1 and a +1, this is a neutral compound. So when we do our double replacement reaction, the two cations that are switching places are actually the sodium and the hydrogen. Those are just going to switch places. So we end up with, we can write it as CH3, COO-NA, or you can put the Na out front. Either one is okay. So sodium now is binding the acetate anion to make it a neutral compound again. And then the other product, now we have 2 H's with the carbonate group. So we write that as H2CO3. Now this compound, this is what is going to create the gas. What you don't know by looking at it is that this compound is actually pretty unstable because the hydrogen reacts so strongly with oxygen that it creates water right away. So we have a side reaction occurring almost immediately, creating water, H2 plus 1 oxygen here, and then left over is carbon dioxide, and that's our gas. So that's what you're seeing, those are the bubbles that you're seeing, the carbon dioxide gas. So this is it's a common combination, vinegar and baking soda for cleaning, and this is actually what's going on. So you're seeing the production of carbon dioxide gas. The production of bubbles when you're cleaning helps to remove buildup, and the acid itself also has cleaning properties as well. So this is our type 3 reaction, the production of a gas. And you saw that list of double replacement reactions that are included with your lab. I highly suggest you work on them. You can also send me an image of those and I can give you some feedback. Good practice for the test. It's not graded as part of this lab, but make sure you do fill in the data sheet that goes along with this lab and submit it on Blackboard along with a picture or a video of you performing that reaction that I just showed you. Okay, good luck and enjoy.